Far out among the countless stars scattered across the universe lies one of nature's most extraordinary creations, the black hole. Today, black holes are recognized as some of the most powerful objects known to science. But the story of how humanity came to understand them is a long and fascinating journey, stretching back hundreds of years. Long before telescopes could reveal distant galaxies, or computers could simulate the collapse of stars, scientists were already asking profound questions about gravity, light, and the structure of the cosmos. The history of black holes is not simply a story about astronomy. It is a story about human curiosity and the relentless desire to understand the hidden workings of the universe. The earliest ideas resembling black holes appeared in the 18th century. In 1783, an English natural philosopher named John Michell proposed the existence of what he called dark stars. Using Isaac Newton's theory of gravity, Michell calculated that a sufficiently massive and compact star could possess an escape velocity greater than the speed of light. If light could not escape the star's gravitational pull, the object would become invisible to distant observers. Although Michell's idea was remarkably close to the modern concept of a black hole, the scientific community lacked both the observational tools and theoretical framework necessary to investigate such objects. And the idea remained largely forgotten for more than a century. Everything changed in the early 20th century with the work of Albert Einstein. In 1915, Einstein introduced his theory of general relativity, fundamentally transforming humanity's understanding of gravity. Rather than viewing gravity as a force acting across space, Einstein described it as the curvature of space and time itself. Massive objects distort the fabric of space-time, and other objects move along these curved paths. General relativity successfully explained phenomena that Newton's theory could not, and it opened the door to possibilities far stranger than anyone had imagined. Among those possibilities was the existence of regions where gravity could become so intense that space-time itself would collapse inward. Only a few months after Einstein published his theory, German physicist Karl Schwarzschild discovered an exact mathematical solution to Einstein's equations. Schwarzschild showed that if enough mass were compressed into a sufficiently small volume, a boundary would form around it. Beyond this boundary, known today as the event horizon, escape would become impossible. At the time, many scientists regarded the solution as a mathematical curiosity rather than a description of a real object. Even Einstein himself doubted that nature would allow such extreme conditions to exist. Nevertheless, Schwarzschild's work provided the first rigorous theoretical foundation for what would later be called a black hole. During the 1930s, scientific understanding advanced further through the work of several pioneering physicists. Among them was Subrahmanyan Chandrasekhar, who studied the fate of dying stars. Chandrasekhar demonstrated that stars above a certain mass could not support themselves indefinitely against gravitational collapse. His conclusions were controversial and faced strong opposition from prominent astronomers of the time. Yet his calculations suggested a startling possibility. Some stars might continue collapsing beyond all known limits. Additional research by scientists such as J. Robert Oppenheimer and Hartland Snyder showed that massive stars could indeed collapse under their own gravity, creating objects from which nothing could escape. For many years, black holes remained purely theoretical. Astronomers had no direct way to observe them, because black holes emit no visible light. However, by the 1960s, advances in radio astronomy and X-ray astronomy began revealing unusual cosmic phenomena. Scientists discovered powerful sources of X-rays originating from binary star systems. In some cases, an invisible object appeared to be pulling matter away from a nearby companion star. As this material spiraled inward, it became superheated and emitted intense radiation. These observations provided some of the first compelling evidence that black holes might actually exist in nature. Physicist John Wheeler helped popularize the phrase because it provided a simple and memorable description of these strange objects. Around the same time, astronomers began identifying increasingly convincing black hole candidates throughout the Milky Way and beyond. What had once seemed like a bizarre theoretical prediction was gradually becoming an accepted part of modern astrophysics. Black holes were no longer viewed as mathematical oddities, but as real and important components of the universe. Throughout the late 20th century, evidence for black holes continued to accumulate. Astronomers discovered that many galaxies contain supermassive black holes at their centers, some possessing millions or even billions of times the mass of the Sun. Observations revealed stars orbiting invisible objects with extraordinary speeds, indicating the presence of immense concentrations of mass packed into remarkably small regions of space. One of the most important discoveries occurred at the center of our own Milky Way galaxy, where astronomers tracked the motions of stars and concluded that a supermassive black hole resides there. This object, known as Sagittarius A, became one of the strongest pieces of evidence supporting black hole theory. The 21st century brought even more remarkable achievements. In 2015, scientists operating the Laser Interferometer Gravitational Wave Observatory detected gravitational waves produced by the collision of two black holes more than 1 billion light-years away. This observation confirmed a major prediction of Einstein's theory and provided a completely new method for studying the universe. For the first time, humanity was not merely observing light from distant cosmic events, but detecting ripples in space-time itself. Black holes, once invisible and theoretical, were now being studied through entirely new forms of observation. In 2019, another historic milestone captured global attention. The Event Horizon Telescope collaboration released the first image of a black hole's shadow, revealing a glowing ring of hot material surrounding a dark central region. The image represented decades of technological innovation and international cooperation. What began as an 18th-century thought experiment had evolved into one of the most significant scientific achievements in human history. Today, black holes remain among the universe's greatest mysteries, challenging our understanding of gravity, time, and reality itself. Their story continues to unfold, reminding us that even in the vast darkness of space,